I don't know how many of you have seen. So in that one, I love snorkeling. I go there. So welcome, come to South Africa, and then you can enjoy. Either you can have like, from the helicopter, how you can jump, So it's experience. You can try to have it right there, right?
If you use the mouse, I guess.
Yeah.
Okay, can you just put the next? Can I give you the, yeah, right. Okay. So suppose you are not doing that way. Again, as I said, like since the university is based on near to the coastal line, so you can do the surfing. I don't know how many of you are interested for the surfing. Not a lot, right? Okay, so surfing is very good, things to do, and you can be in the sea for like 3-4, hours right there. You can do. Otherwise, you can do the African safari. African safari is one of the adventurous. Those who is connected with me with my phone, like phone number, you can check my status or go to my Facebook profile. I always do. I sometimes walk with the lions, sometimes having interaction with cheetah. So that is like beauty of South Africa. We do. And the idea is that you should visit and you can also enjoy the same one, right? But again, it's not like I have trained the lion. No, it's because the people who trained, they try to do it, and obviously they have to charge, right? But you can take your own car and you can do just like the peoples are doing. This is like a typical safari. I usually use my own car to drive so that I can spend more time with that. I have recently took actually some videos and picture. Dr. Avnish is there, and then when I put a video, and then he says, just run away, the lion is next to you. I just say it is not going to happen because they are trained like that. And there is a feeding time and you can really enjoy like that, okay? Now, the idea is like the party is over, right? Now you are chill up, right? So let us try to talk about like little bit about the nanotechnology, right? So we can try to see how the material is going to go. So how many of you heard about this buckyball? Okay, so the idea is like why it is that very much important. No, nobody knows the properties right there. Okay, I will go a little bit later, but do you know the full name of buckyball? Right, so whose was Buckminster? He was not a scientist at all. He was an architect. He is the one 5 years before when the buckyball was discovered, that is C60, 60 carbon in one unit they have displayed, but they don't know how to crack the structure of that one. And what he has created, you can Google it, he created a dome structure. Okay, there is a stadium right there in Europe. He has created before this buckyball was discovered. So that dome structure, and that is how like when they were trying to configure this buckyball, they put it just to honor them. They make this name as a Buckminster Fullerene, right? So now how it is going to be looking like. So can you just put to the next one so that we can see how the nanotechnology is going there. We can go a little bit very quick one, okay, little bit back. So if you are looking about the nanotechnology, many of people are like working, so it will be useless for them. But those who are not working, especially the student side, so then you can try to imagine. Do you know imagination is more powerful than knowledge? Is it correct? Who said that? Sir. Okay.
Sorry.
So Einstein says imagination is more powerful than knowledge, but he also says something else. He says knowledge is inversely proportional to your ego, isn't it? So maintain both the things right here. So try to go in the imagination way. You can see the size of Earth and try to see a football. Nowadays, it's very popular, right? So if you see that imagination, then you can try to see the fullerene, right? So you can see how small it is, right? If you look your hair, 10,000 times smaller, right there. Your DNA, it's around 3 to 12 nanometer size, right? So the many things is right there existing in terms of the sizes. We have to go quick, otherwise chairperson is going to throw me away, right? So in the scale, we go 10 to the power minus 9. So you can, okay, you have to go forward, yeah. But this is important for you to understand like how it is existing in your daily to daily life. Look at that, human fingernails grows 1 nanometer every second. Have you know that? If you try to see a beards of a man, 5 nanometer every second. So those nanotechnology we are practicing every day. How much smaller it is going there, right? In terms of like how many of you like the money, right? 1 billion, and you're looking comparing with 1 rupee. That is the nanotechnology we are talking about, right? So we have to, see actually like how those things are going to, affect the properties. So the nanoscience is something like how you can manipulate, how we can engineer. So those are the things I'm going to talk about, because I already spent around 5-7 minutes to introduce unnecessary things. So the idea is like why we are looking, because we are looking for the reactivity, we are looking for the size, and we are looking for the magnetism, because of their very, very enormous and attractive properties based on their application of the material, right? So I'm not going more details. Obviously, you guys are more smarter, so you will know a little bit later. Otherwise, you interact with your question, then I will try to explain a little bit, because this is more generic. Next one. Right. So, but whether nanotechnology was existing nearby you, have you seen somewhere? No? Have you visited Qutub Minar? Have you seen the Asoka pillar? There is an article published in 2002 in Nature, right? You try to see, they have concluded, not us. We worship because Qutub Minar is us, right? But there is a famous scientist, they have done and they published, and they have concluded like it is carbonaceous nanomaterial they have put it. But if you see the Tipu Sultan sword, if you try to see this Ajanta painting, it's all going there. But whether we have to talk about like Feynman, when 1959, he was trying to, make certain kind of, a speculation how it is going to go, or when there is an official term come in 1974 by Norio Tangwitz, right? And after that, I think the carbon nanotube discovery came, and based on that, after that, I think we are all going more further right there. But we were all using in different kind of other perspective. If you visited many European country, if you see their churches, in our side as well, many temples. How many of you have visited Jaipur? Jaipur Palace, or those kind of palaces, if you try to see with their decoration, they used to use some gold nanoparticle with that way, right? So that's what in the sunlight, how it is going to reflect. So obviously that science was quite good that time. Obviously, I don't know whether they knew whether it is nano or not, but obviously like they were doing. But in the European side, if you try to see it, like they were using quite a lot of things. So right. So what is going to happen today? Like how we have to say certain things, which is going to say like it's smart, just like I was trying to say. Have you actually something definition about smart? Smart and nano can be together? Yes, no? Very good. Yeah. So let's see actually how it can be together. When you wake up in the morning, right? Go and try to see yourself in the mirror. How does it happen? Are you going to recognize yourself? Yes. Because obviously like your hair is somewhere, your face is, you are going to brush, nice to put some, So what you try to do there, you are changing the physical parameters, right? Suddenly when you come with nice dress, somebody says you are looking. Is it not your part of your life? Right? So what you are trying to do, you are trying to engineer yourself in the smartness by changing the physical parameters, right? So in that scientific term, what we are changing like physical parameters like pH, temperature, time, so those kind of density, so surface density. So all these kind of, parameters when we are trying to change, that's how the material is going to exhibit a characteristic properties based on the application, what we are expecting going to be enhanced multiple way, right? So it is not going to happen like it's one property, it is going to happen, it is going to have the multiple property. The best example in front of you, can you see? Now, everybody is on there, isn't it? Looking on your phone. The best example of a smart material. Why? Because your same phone, you can do the video recording, you can make a call, you can do the WhatsApp chat, all kind of multiple, And the recent example, like 3 days back, there is a Nobel Prize has been, awarded. Do you know where? Which area? Quantum dots, right? What is quantum dots? It's around the size is ranging from 2 to 10 nanometer, right? So obviously what you are trying to do when you are changing the parameters, you are also trying to change certain thing, which is surface to area ratio. It is also going to change, and that is dramatically is going to be affecting on the material characteristic, right? So what I try to do, I will just try to go back like what I am going to, say today in few minutes time. is like we try to make called composite material. Okay. So if you try to understand yourself, do you know what is composite? Have you heard about that? Who said yes? Hmm? Very big science. I don't need big science, right? I just need a small science, right? Because if you know the small science, you can do the big science very big way, right? So idea is like if you are trying to look about the composite means mixing of two things together, right? One is going to be your reinforced material. The other one is going to work like a matrix, right? So now what you are going to reinforce, which is going to be your filler, okay? What size it is going to hold, that is the one it is going to bring the smartness properties in your material, right? So one kind of material today I will share you is like certain kind of nano composite material where we try to bring the band gap down. That's how I'm going to head there. But let's see. So example you have seen there with the smart materials. You can go next, right? The microchips are there. Go next. Yeah. And you can also try to see this kind of, more application, but I am more focused on the water because that's my whole area of research. Go to the next one. Because why I am trying to focus more on the water, because is this the problem you are aware? How much available of the water we have it? Do you know 97.1% of water is covered by the sea, right? How many seas there? 5, 7. You remember still the song, right? So there is a 5C and it is going to go 97% of the water. And based on that, if you are trying to see lake, borewell, and then you are going to have the rivers, ponds, all kind of things is also connecting close to 2%. So what is available? It's 1%. Around less than 1% water is available. And what we are trying to make the problem with that water, see, who is creating this problem? Is it not us? Right? So what you can do, let's go to the next and see. So the idea is like that I was supposed to have one more slide, but so the idea is like what you are going to do actually, you can try to minimize yourself, your activity in terms of like saving the water, right? So what slide I have not provided here, I just wanted to share with you that how you can minimize the saving of the water. Like when you are cleaning the dishes, you can try to minimize there. If you see the normal toilet flush, do you know how much water it consumes? 60. Who says 3? For one number or two number? For every one number, it goes 3 to 4 liter. But if you two number, it goes 17 liter water. So you see how much water you are wasting. So what you can see, you are an engineer, the future engineers right here. What you can think actually how you can channelize so that you can treat the water and you can reuse it. People are doing with the washing of your kitchen things. So they are trying to do like rerouting, especially in the Europe. I have a very good collaboration in Cranfield. What they are trying to do, they are using photocatalytic material, what I will share just now. And with that one, they are using the same water for the irrigation purposes, right? So now I'm going to start. Chairperson, please forgive me. I'm just taking a little bit more time. So now the real work, what I wanted to say is called photocatalysis. The last session, somebody already introduced with that way. So what is happening with the photocatalysis? You are looking the sunlight and it is going to the material. One material I'm trying to talk about here is titanium, right? And it is going to, create. One is going to be called like a hole. The other one is going to call it. Everybody is blank. It's written right here, right? So the idea is like when we are going to put it there, the sunlight is coming, falling on the surface of titanium, right? So when it is following there, here it is going to create the holes, right? And then the other one, when it is going to go in the excitation state, that is how you create the free electrons, right? And they are the one who goes and then try to degrade. What is degradation? It is happening. We try to focus in this kind of work. I will try to share with you a little bit on the pharmaceutical waste, but we try to do with the textile as well. So idea is like everybody here looking so smart because of your clothing as well, right? So clothing, it is going to need more of your dyes, right? So those dyes, like whether it is disperse dye, azo dye, wet dye, modern dye, so different kind of, dyes are there, which is also creating a lot of, havoc situation, especially azo dye is more anti-cancerous type of, properties they try to exit. So the idea, what I was trying to say, like when you are creating the holes right here, how you are going to minimize the recombination, right? So that is the band gap. I was chatting to my colleague last time, which is like how you can like minimize the band gap. So that is the whole idea, because you can maintain the synergistic effect, right? The constant flow of electron we have to maintain right there, okay? So what is happening actually, and I think that has been also explained in the by previous speaker, but let me just try to, go and try to, share with something what I wanted to do. Like if you are looking around the UV visible light from the sun, it's around 50%. I think that's what has been told actually right there. But again, you are going to see like what kind of visible light it is going to go, right? There is some news used to come like, there is a UVA is in progress, right? UVV is in progress, UVC is in progress, right? If you visit some European country, even in South Africa, there is a chamber called UV chamber, because the problem is the white people, they have the problem with the melanin, right? So with that one, they try to take that, the UV, bath, what you call, so that is the way they try to maintain their skin, that way. So the whole idea is like when we are trying to have the material, we are looking in that way, like it should fall in the visible range, right? Because if we are following in the visible range, obviously we can use the direct sunlight, which can degrade the material so easily, and obviously we are not going to look. Most of the people who is working in this area, I'm not challenging, but mainly they are going in the UV range. That is, you are looking there 200 to 400, but our target, like let us go to 400 to 800 nanometer, and that's how like this work is getting there. Okay. So the idea is like what we are trying to make it like, we are trying to make certain kind of nano composite material, which is based with the carbon nanotube, and then we try to use some rare earth element, right? So in this case, what we have used, actually we have used the erbium. I think if you know the lanthanides, so lanthanide, you can find this kind of element right there. And the idea is like we took first the titanium. So three kind of mechanism is right here, what you can see. So one with the titanium itself, how the degradation is going to happen. Then the second, what we incorporated, like we incorporated with the carbon nanotube. Thanks for my colleague actually, who has presented about the CVD method right there in the last presentation. So in that, when during the process of making this titania, I try to do the CVD so that we can generate the carbon nanotube, so that we can get good assembly and the good orientation of the molecule right here. And after that, we try to embed the erbium, right? So that is just like a mixing of the material. We do the microwave assisted method. I think the detailed paper, you can read it. This one we have published in Applied Catalysis B, a little bit long back, I think 1 year or 2 years back. And then you can try to see. So the idea is like how we can try to see between the valence band and the conduction band right here, and then how you can try to minimize the recombination right here. And that is why all kinds of a doping is happening, whether it is a P block doping, it is happening. People are using like nitrogen, sulfur, many kind of other P block elements people are using right there. And you might have seen the carbon nitride as well. Now, some people are also trying with that. Our group also tried, but sometimes my students sometimes say like, can I do the reduced graphene, reduced graphite? The idea is like, what is your target, right? So let's go to the next one. So that one is like when we try to embed this kind of a material, this is the morphological, not going detail because this is the simple scanning electron microscope that show you the surface morphology, right? And then obviously, if you try to see the XRD, you can see the nice good band gap. Again, because of the nature, it is still in the amorphous in nature, not very much crystalline in nature, right? So go to the next one. Right. So you can see actually what was the whole idea behind making. And I'm very happy to share with you, like this work is also, being very much interested with the Toyota group in Japan, because they're looking this kind of material actually just to put in their own company, actually just to see like what they can do in terms of degradation of the stuff, right? So what is happening, what we were not happy, but still the paper got published in the Good Impact. The idea is like it is taking high time. If you are looking for 97 to 99% of degradation, it is taking around 180 plus minutes, right? But the maximum degradation, if you try to see from this kind of graph for the reactive rate RR, this is very big, good dye. You can also try to see. We have done quite other kind of things right there, but you can see like the decomposition is happening around 180 80 minutes. So that is the little bit challenge we need to look actually like how we can minimize the time, right? Okay, carry on. Okay. It's not moving. It's saying time is over, right? So what we try to do, that was just little bit small flavor I give you, right? So we try to do it like how we can do. How many people are working in titania here? Titanium nanoparticles? You're not. Okay, we have seen from the speakers right here, right? So the titania, how many, because the question was not that, the question was like, how many form titania does exist, right? So usually it is in 5 form, it does exist. So we try to manage it to like when it is changing, usually the most existing form is the rutile, right? And then you can convert to the anatase. Yeah, you did 5. Oh, sorry. Right, okay. I will try, thank you.
Yeah.
Okay, so what we are trying to do actually in this work, we try to make the changes of the phases of the titania, how it is going to affect on the band gap, right? So the 5 phase of the titania, we are not talking here, we only talking about the 3 phases, which is the bruchite anatase, then you are looking the rutile anatase, and then you are looking for the rutile anatase. And this one we were trying to do with the direct sunlight, all of them. And here we were trying to do actually like, we were trying to introduce certain kind of element, which is called sodium chloride. So sodium chloride, when we were trying to put, suddenly the band gap was quite reducing. Obviously, we were trying to minimize the recombination right here. So in this kind of a case, you can see it is, and then we try to incorporate like little bit more the iron forms, right? Both +2 and +3 kind of forms we try to do there, and we can see like how the from the valence band to the conduction band it is going to change. And obviously what was playing the most important role here is the sodium chloride, what is right here, and this one it is going around 10%. When we are trying to put the 10%, in the next slide you are going to see there like how much immediately the band gap has been changed right here. And then suddenly when we are going for this one, when we are putting the direct sunlight, you can also try to see in the rutile anatase phase, and we are changing the percentage of the iron as well as in the titania and how it is going to affect. Go to the next one. So you can see like we have done nice, good XRD actually patterns right there. So that's quite easy actually for you to understand there. Like it's a good morphology we are trying to see. Obviously, we are trying to see like whether it can be more crystalline in nature, but obviously there is a amorphous, because of the material itself. We try to see. This is the way how the molecule, the material is looking like. So the size was close to 40 to 50 kind of nanometer. We try to avoid the agglomeration, but obviously we were not using a lot with the reducing agent. So obviously that is the problem we had. So a little bit agglomeration you can also try to see there. So now this is the beauty I was trying to talk about. Like if you see titania itself is around 3.21, that is the band gap we are looking there. And then when we are trying to change the percentage, you see this is the 10% NAF, and then from 3.21 it changes to 3.08, right? And suddenly like when we are putting the sodium chloride around 25 with the iron content 25%, we got from 3.21 to 1.67. And that is why I was asking you how we can try to bring the band gap around 0. Obviously, we never wanted to use the graphene, right? In this kind of work, because graphene is the most abundant material at this moment, right? So this work was quite important because we try to take certain kind of SMS, that is the pharmaceutical waste, we took it, and it's almost like 100% decomposition happened. And so that is another kind of solution we can try to give. And we can also try to incorporate certain ways in terms of like the beauty products, the beauty product, how you can try to degrade. So we have also one of the applications right here. Since the chairperson is saying like I have less time, so I have to quickly try to go there, right? So some of these work, actually, some of the postdoc peoples, what they are trying to do, actually, I will just highlight. Not will take 2 to 3 minutes, right? So we'll try to see there, like we are putting as a more adsorbent filter or kind of a membranes. That is the research we are trying to do. Actually, I wanted to talk more on the membranes, but when I see 25 minutes, then I said like it's better one segment I can talk today, right? Especially you enjoyed the first segment. I don't know how you are enjoying this one, right? Okay, so we try to make like with the zeolite, because zeolite is most abundant material. You can easily try to make it based on, like again, changing like how the ratios you are, bringing there. And again, like zeolite also have like self-cleaning kind of, mechanism itself, right? And so we were trying to use, and it is working quite well there. Then certain like with the mesosporous material, we are also trying to make it. I think in this one, we are having like titanium, silica, both together. So I think we missed silica right there. But we have like a silica, titanium both together, and we are trying to see like how this zeolite is playing the big role. And this is also very good work we are trying to do. Again, right. So the idea is like, if it is working for the small fragment, how it is going to go for the bigger structure. If you can also try to do like, if you're looking for the dye, can it go for the 1 liter to the 25 liter? And what kind of industry is interested? So those kind of elements, we directly work with the government as well as the industrial partners. So we do actually those kind of video. I skip it. Next time we can, share with the, that way. So the whole idea is like how we can try to go for the more industrial application, and also the whole idea hot sharing, like we can also go for the domestic purposes, right? So this photocatalytic material can be used for the domestic purposes as well. Can you go to next? So that was my little bit request from the chairperson, like give me another 2 minutes, just little bit introduce. This is IEEE, I'm heading as a Nanotechnology Council. So since 2014, I am the chairperson. Nobody is coming, taking, usually it's only for 3-year position, but nobody is coming. So I am the one who's taking over. So nanotechnology, IEEE, know everybody? Is the Institute of Electrical Engineers and Electronics, right? So with that way, whosoever is doing the, the engineering program, you have to be, quite aware, become the members, right? And when you are involved with the nanotechnology, you can also affiliate with me, right? If you are affiliating with me and you want to visit me, I'll give you your travel as well as the accommodation for free. Okay, if you have to register by yourself, right? Unless somebody make it free. Okay, if you want to do certain community program, you can select certain areas and you can see like, I am looking for $1,000. That is my jurisdiction. I will give it to you, right? But I need the pictures, videos, everything, whether you have done or not there. So why I'm sharing this one? Because money is there now. Now you need to understand next one is like 500,000 members are there, quite big organization. Next one. You can read actually, all these things because I just took 2 minutes, right? Okay, so the idea is like, then I have my own company. What I was trying to say, like Academy of Nanotechnology, there is a YouTube channel, there is a website, so you can also do, but this is like more charitable. Whatever income we generate, we try to donate so that people can be, quite, helping. So we do provide consultancy, summer school, teaching courses, so many activities are there. You can be, quite connected. Next one. So these are something you can follow. Go to next one. Yeah, so you can follow certain things. I have been introduced to by chairperson. So I'm providing the proof chairperson so that people can see the last one. Yeah. So then with the, I have done there, the very last one. So these are one actually came this year already. We got 5 for this year. It's not the number, it's just like what it can make a difference in your life, right? Next one. So I think it's not updated, but I have to update this one. So I have to thank my most of the collaborators all over the world. It is there, right? And without that, it is quite impossible. I didn't put my group members at this moment, but I think that is going to be, saying thank you with the next slide. Next. Yeah.
Thank you. Thank you. Thank you, Professor Ajay, for this wonderful journey of nanoscience. It's very apt for this audience because you started from a very fundamental level of what a nanoscience or nanomaterial is, and then went on to show the vast kind of applications and implications to society, especially for this kind of technology. Thanks a lot for going through this entire journey. Any questions from the audience? The seminar is open for discussion. We can have 1 or 2 quick questions.
And the questions should not only go with the scientific, you can also have the non-scientific, right?
Absolutely.
Non-scientific, like how to get registered, what to come as a PhD student, you can contact, those things I do, it's like say, okay, so if you contact, you have to contact with certificate, right? But let's see if you have any questions. If you don't ask, I will just say like I didn't do a good job, right?
Yeah, please.
Really, it was a very informative and wonderful lecture. I have only one, not a question, it's just a query. You have pointed out the conversion of different form of titanium by light induced. So normally we have it, we are heating thermal induced conversion of anatase to brookite to luteal. So is it possible by just irradiating a light, they are going to convert from another form?
Yeah.
This is my query, sir, not a question.
Many people are doing, so these are trying to do with the microwave assisted, and we are using the, hydrothermal bombs right there. So we try to put it like all the 3 set of the hydrogen bombs right there. So once we put in the microwave, so we try to activate the molecule right there. And then after we put in the hydrothermal bombs, so obviously, it gives. So conversion is quite right. Yeah, because it goes like very high temperature, suddenly suits that. So thank you.
Any other questions from the audience, students especially? It can be non-scientific as well, like the speaker said.
Maybe I would like to say, sir, thank you so much for the wonderful offer. First, I would like to say you have given an open offer to everybody to come to South Africa. I think that's a wonderful thing, I'll say. Beyond the lecture is wonderful. And your place where you're working in a nanoparticle. So I think we will be more interested how we can bring our student there. So that will be my question as a, from the organization.
Okay, just to bring yourself and student, it's very critical and very good questions. So there is a lot of program, why you want to come there. First, if you want to come there as for the roaming purposes, that like little bit on your personal touch, I will take care, the local side, right? But if you are going by the scientific purposes, there is several kind of platform. The bilateral projects are there, which call like India, South Africa collaboration. There is a IPSA, India, Brazil, South Africa program. So you can also come from there. Currently, there is a very nice open program called BRICS, right? So the BRICS is open, so you can also participate. But again, the 6th theme, what they have displayed, they are mostly targeting about the climate change and those things. So if you are looking there, you can also look there. The very easy one, what you can try to do is called internal funding, right? So internal funding, like you can approach to your principal or, so then they can also try to put funding. We can also put funding, and you can also try to send the student, and they can also. What I try to receive actually most of the BTech student, which is on the 3rd year, when they are about to BSc 30-year honors, they try to do certain projects. So obviously we have to take care and do. Also, if as a faculty member you want to visit, there is a very nice DST program called SIRE program. So with that one, you can also try to come and visit, and very nice funding they used to provide. Community development program, even IEEE, where that is the very easy way of just like make sense actually how you can try to do. Thanks a lot.
Now we would like to felicitate Sir, and for that we would like to invite Professor Subramaniam and Sir Anthony, sir, please kindly felicitate with the mementos and a bag. Thank you so much, sir. Thank you so much, sir.
So we'll now move on to the next speaker of the session, Professor Tanmay Basak. He's a professor at the Department of Chemical Engineering at IIT Madras, which happens to be my alma mater as well. So a lot of nice interactions over a very short period of time that was happening. Thanks a lot. Tanmay Basak, it's okay. I think I'm audible. Oh, okay. So Professor Tanmay Basak did his bachelor's in chemical engineering from Jadavpur University before moving on to ISC for master's and PhD. And subsequently, he was a NSF postdoctoral fellow at University of Massachusetts at Amherst, and then EPA postdoctoral fellow at University of Houston at Texas. And Texas, for example, Houston is the place where, if you have seen this Apollo 13 movie, Houston, we have a problem. So the same very famous place for space exploration. And he was a visiting faculty at IIT Madras, and then subsequently moved through the ranks as assistant associate, and then now he's an associate. Yeah. Oh yeah. Okay. Assistant, and then directly he went on to become a professor at IIT Madras, where he continues to work and get associated with. He's also an associate editor in International Communications in Heat and Mass Transfer Journal, also International Journal of Heat and Mass Transfer in Elsevier, visiting professor at the School of Computer Science and Applied Mathematics at University of Witwatersrand, Johannesburg. He's got numerous awards to his credits: Academic Excellence Award, Young Engineer Award, Diamond Jubilee Young Achievers Award, Nasi Scopus Award, Herdelia Award, member of Indian Society of Heat and Mass Transfer, Institute of Chemical Engineers, and reviewers for several other journals. So with that brief introduction, I'd like to pass on the mic to Professor Tanmay Basak.
Thanks a lot, and it's good afternoon to all of you. And of course, you are not hungry, because also I am delayed by 1 hour. That's okay. And thanks to Professor Pratibha Kumari for giving opportunity to give lecture here. And of course, my background is chemical engineering, and based on the conference theme, I chose the topic. I can assure you that I cannot put you in sleep. I can keep you awake. Check. Okay, I had been listening to the light wave, the solar, the ultraviolet, and of course, previous talk was partly on microwave, and I will be talking about enhanced efficient microwave processing of materials. So all the common format is they're all electromagnetic waves. So electromagnetic waves, it has light, even the visible light is electromagnetic wave. Even the gas oven, you can see the wave, that is also electromagnetic wave, microwave, electromagnetic wave. So all electromagnetic wave. So before getting into details of microwave, let's go to the next slide, and we'll see the electromagnetic spectrum. So what is that? So you can see the different band. This is the, you can see the frequency, and this is the microwave, this is infrared, visible, ultraviolet, X, and gamma ray. And when and today I'll be focusing on mostly heating. why I chose it, you can all understand. Everybody's kitchen has microwave, and quick processing. You open the door, you put the materials, and within few seconds, few minutes, not only maximum 1 minute, you can have your food processed. But there are different kind of interesting episodes. So my talk will be completely focusing on the heating application, but I will go for something way forward when I will choose the material which will not get heated by microwave and how to heat them. That's the challenge, because if it is getting heated, because everybody's home has microwave oven. We can just cooking purpose, anything you can use. That is not a challenge. Challenge is a material. Which material? For example, you should not put metal in microwave oven, dangerous. Microwave oven will go in 1 second. In fact, some of the oil substances, alumina, if you put in microwave oven, they cannot heat up. But we have to use microwave. Why? Because microwaves, if it's getting heated with some kind of technology, it can dramatically enhance the heating rate. So these are interesting episodes. We'll talk more in the journey of my lecture. Next slide, please. So typical microwave generator, magnetron. We are not talking about design, but if people want to know what is inside in the microwave oven, you can see the anode vanes, cavities, cathode, electron cloud, waveguide, and so on. This is the whole spectrum of the microwave oven. Next slide, please. So the microwave material interaction. What actually happens? We are talking about the heating phenomena. When, for example, I have the light, if I put my hand here, this is the microwave, this is the electromagnetic wave, okay? My hand is not getting heated, okay? Even the X-ray which just passes, imagine that X-ray heats up, your entire body will be burnt out. So when you should not put your hand in the microwave oven, it will be burnt out, okay? I will come across slowly why all electromagnetic waves, but microwaves do the dot on heating part. Let's focus on that part. And for that purpose, we need to focus on the microwave material interaction part. So there are different kind of episodes when microwave passes. So this is the absorbing materials, the transmission. So when this is like a wave, you all know light. You have seen the physics of light. It has got reflection, incidence, reflection, and of course some will be going by transmission. When it is absorbed in material, what actually happens? Absorbs and it won't get reflected out. Transmission means it will fully going through. Reflection means fully reflected. Is actually metal falls in this category. Metal does not absorb microwave, and scattering, it has got reflection, all those. So these categories you can just see here. Open, so metal. So as I said, that metal does not absorb microwave, and that is dangerous. So whenever microwave passes through metal, not passes through, it just hits metal, bumps, and then magnetron will be attacked, and microwave will be completely gone in oven, will be completely gone in few seconds. And then transmission, so transparent material, low lossy material, glass, ceramic, air. So air, it does not absorb microwave, and that's the beauty. Because of that, microwave communication, when you have all these communications, all this, TV, all the mobiles, everything is microwave communication because of air, does not absorb microwave. Imagine that if air absorbs, in fact, I can tell you that when you have a cloudy sky, you can see that your Wi-Fi does not work that good because of the moisture, and that absorbs microwave, and the signal will not be smooth. In fact, in my home, I have seen the experiment. I have the Wi-Fi, the cloudy sky, it is raining. In fact, I have to go to the very near to Wi-Fi connection to get my connections up, otherwise it is a problem. So air is, so dry air, I should say dry air is transparent, and of course glass, ceramic, absorbing high lossy materials, food, silicon carbide, and water. So I was talking today, the water is very highly absorptive material. Interaction between materials and microwaves are very, very interesting, and that poses, that understanding is very, very important, and to pose a challenge on microwave heating. And of course, the dielectric response. Dielectric response is very, very important. Dielectric polarization loss, and that entire physics gives the scenario, the outcome on the microwave heating effect or pattern. Next slide, please. Okay, so that's the mechanism. So what actually happens if the visible light, if you pass, it does not give any heating effect. If microwave passes through, it gives the heating effect. because of the frequency range, and it gives the polarization effect. And we have the different kind of polarization effect. Electronic polarization, if you have no electric field, is the structure. If you have electric field, gets distorted. Atomic or ionic polarization effect, you can see that. I'm not focusing much because our focus will be on orientational or dipolar mechanism, because you can see the dipoles, they're all randomly oriented, plus minus. When you pass the electric field, which is oscillatory electric field, and they will try to orient along the electric field, and they will try to rotate, and they will try to have frictional effect. So that means if you do this kind of friction, you can see the heating effect, and that is called dielectric loss. And there's interfacial polarization. So we have the dielectric constant and dielectric loss effect. So this is the interfacial polarization effect, and our zone is this highlighted zone. I'm not going to discuss much about that part, and you can see the orientational polarization. And these are frequencies, very, very important. The frequencies around so basically domestic microwave oven is 2450 megahertz, and that's the all Indian setup we do. In fact, US have seen some different kind of frequencies, but this frequency should not interact, so that with the microwave communication is should not be disturbed. So with this frequency range, this is the orientational dipolar polarization. In fact, if you look at the dielectric loss, which is very interesting, if you see this zone, there is no dielectric loss, is very less. And this is the part we are seeing some kind of maximum of dielectric loss. And that's the interesting part. So that's what, when the visible light is there, it goes to different kind of zones where dielectric loss is zero. The dielectric loss is zero or negligible. There will be no heating effect. And that's why that's pretty interesting. Although all our electromagnetic waves, microwaves give the heating effect because of this dielectric loss. So the overall mechanism, there is no dipole moment in the absence of electric field. As you can see, that dipolar polarization occurs in the presence of alternating electric field. Of course, alternating electric field orients asymmetric polar molecules, dipoles, of course, rotate, and it gives the frictional effect, dielectric loss. Next slide, please. Next slide. Yep. So dielectric properties of water. So there's a classic example, as I'm saying, that water is a beautiful material. It has got tremendously high dielectric loss. If you put water, it will evaporate. It will get heated up very fast in microwave oven. It is actually some few seconds. But interesting part is oil. If you put oil, it won't even heat up. Why? That is the dielectric loss. That is dielectric properties, which can explain better. In fact, I have done some theoretical work, very interesting work. Oil water emulsion heating is a very interesting part. Even oil in water and water in oil, it will behave in a different manner when you put in the microwave oven. Next slide, please. So this is a summary what I was talking. So overall, we are talking about the heating effect. We are starting our talk from the kitchen, when we put the different food stuff and get heating, and we are going beyond to the materials which cannot be heated by microwave, but can be heated with the help of assistance we call as susceptor. We'll come back to that. So dielectric, previous slide, yes. Dielectric properties, dielectric constant, the dielectric loss. So constant is like a spring dashpot model, and dielectric loss I showed you. This is the rubbing the hand, and this is the typical dielectric constant, dielectric loss property, the frequency. And of course, these two materials, these two parts, we have to focus: volumetric heat source and shorter processing time. Next slide, please. I don't get into much on the mathematics, then you all leave the room, but you have to show these are the physics-based, these are the equations, Farade's law of electromagnetic induction, Ampere circuit rule, Gauss's law of electric field, Gauss's law of magnetic field. These are the basic equations, and these are the boundary conditions of the interface. And if you combine them, you will get this kind of equation, which is called as Helmholtz equation. And you can, of course, go through my papers where we discuss much on that. And microwave heating is based on this electric field, and you get this cute formula is half omega epsilon 0 kappa double prime dielectric loss and electric field and electric field complex conjugate. And these are very, very complex quantity. In fact, electric field is a complex quantity. It requires a lot of mathematical challenges, and we can also have closed form solution and numerical solution. Next slide, please. So how the flow of microwave power just on understanding, we need to understand microwave propagation, talking of dielectric materials, orientational dipolar polarization, role of dielectric loss, and induced electric field and volumetric heating effect with the materials. That's the final outcome. Next slide, please. So the why microwave? So I have already explained conventional heating. You have just put a burner. So what actually happened? Burner, when you get the heat, that is also electromagnetic wave, but it does not penetrate much within the material. So it's like a surface heating. But when you have microwave heating, it penetrates within the material, and because of the ionic polarization, these two will be pretty active, dielectric constant, dielectric loss, and this gives the depending on the value of dielectric loss, you have the volumetric heating effect, and you have the two length scales, wavelength and penetration depth, which decide the heating quality, heating properties of the materials. Next slide, please. Various microprocessing applications. Based on that, we had material processing, waste treatment, medical sciences, and to control process equipment and compactness, cost, maintainability, improved safety, energy savings, enormous. We'll be talking much on energy savings today. Why microwave is actually used for energy savings, and I'll be discussing a lot of experimental episodes to talk about how much energy savings, and that has been published a review article in Energy Journal. And summary, as you have seen, the volumetric heating, selective heating, lower pollution, lower processing, these are the typical advantages. High temperature capabilities. In fact, if you want to sinter materials, microwave sintering of materials is a hot topic, and very high temperature you need to achieve, and microwave plays enormous amount of role to achieve a high temperature within few minutes, and which can be achieved in few hours by conventional burner. I'll show you some of the results. And of course, next slide, please. Okay, so microwave processing of materials, microwave techniques are used to process the materials, ceramics, polymers, composite, minerals, and powders, a typical microwave setup. Next slide, please. So metals, oxides, carbides, borides, silicates, porcelain, these are also materials can be processed. Next slide, please. Yes. So I have introduced the term called susceptible. Why it is susceptible? Because when the material like alumina or zirconia, this type of materials, what actually happens, if you put in a microwave oven, they won't be heated. So in that case, microwave technology cannot be exploited. So what actually we can do that? There's another material called silicon carbide, which is a very interesting material. The silicon carbide, what you do that if you just put it within few seconds, it can reach even 500, 600, and so on, and based on the purity. So that we call a susceptor, and we can actually put say silicon carbide with the material. Silicon carbide will absorb the heat. It will transfer the heat to the material which is being heated, and with that we can have enhanced processing, which is the agenda for my talk. So the direct microwave heating, when you don't have susceptor, it will be just propagating, and based on the constructive or destructive interference, because a lot of waves will be propagating, a lot of interesting physics. I am not getting into that. And of course, when heating occurs, it can be occurring. Heating front can be propagating from the inside. It is not like heating front will be propagating from the outside. That depends on different kind of wave propagation. When you have susceptor, so the susceptor material here, the susceptor will absorb much heat, and heat can be propagated from the surface, and also that some of the part can be transmitted, and heat can be also propagated from here, and that can be the two-way heating, and we can have uniform heating property with the susceptor. Next slide, please. So susceptor assisted microwave processing is our main focus, and is of course the two-way heating. The susceptor absorbs the microwave energy, converting them into thermal energy. Heating due to the microwaves occur from the core of the sample, but the susceptor provides additional heating from the surface to some sample by conduction. Of course, the efficiency, more uniform processing, reduced dependence on the material properties, smooth processing. Next slide, please. Okay, so these are the susceptor design. How to design the susceptor? The rod-like susceptor. These are all silicon carbide rod, a sample. And what silicon carbide is? The sample does not heat much if you just without susceptor. If you put the sample, it doesn't heat much. So susceptor actually absorb tremendous amount of heat, and it will radiate the heat, and sample will be heated. It's a very interesting setup. Powdered susceptor. This is you can see susceptor, silicon carbide susceptor can be here, sample can be placed here. This is a microwave oven setup, and susceptor tube. These are all susceptor material, and sample is actually here. So the essence of this part is susceptors are the high lossy materials such as silicon carbide, carbon, molybdenum, silicide, zirconia, which can couple with microwaves even at the room temperature. Susceptors are generally incorporated as the secondary heating elements, And the supporting plate or the sample holding crucible can also act as susceptor. So challenges, as I said, that susceptor design is critical to achieve optimal processing, of course, should provide the required initial heating, but should not shield microwave from the sample in order to allow microwave material coupling in later stages. How many minutes I have? 10 more minutes. Okay, next slide, please. So the lead zirconium titanium, so it's one application of susceptor. This is one example is for the lead zirconium titanium plate. What we can see that this is a very interesting stuff. So when we are heating the material, so core is more than 400 degrees centigrade hotter than surface, and surface is not that much heated. So that is a direct microwave heating, and this kind of non-uniform heating is not warranted. It's a material processing, a dangerous thing. So susceptor assisted microwave heating, it will lead to the uniform heating from the core to surface. You can see everywhere, core and surface, the temperature is same. And this is a setup we have used. We have been focused, not that you have used, we have actually trying to focus the enhancement. The paper was published in 2009, and this is a silicon carbide rod, and it has been very interesting. Similarly, the result has been looked at for metal oxide doped zinc oxide pellet. The same scenario, core and surface, the big temperature difference. This kind of heating is not required, not warranted. So we wanted to have uniform heating, and also, of course, susceptor, when you place this kind of setup, it can give the uniform heating stuff. High purity aluminum powder. This kind of setup we have used. This is setup is a mullite fiber aluminum board, and SiC susceptors, of course, the thing. And these are the scenarios we can see the conventional versus hybrid microwave heating. Next slide, please. Direct microwave heating for the cesium and zirconia, and it's very interesting what actually happens. This kind of materials, if you put, it will not heat at all, but after some time it start giving plasma. It is dangerous. So what actually happening the long warm-up period, and it will give the highly oscillatory heating. But if you have this silicon carbide thick SiC tube, this is a different kind of design. This is called engineering design. We need to have different kind of, we have to play with. There is no such hard and fast rule. What is a susceptor setup? What kind of susceptor assembly? And this is my very interesting consultancy projects. People approach to me. I just give different kind of susceptor design by seeing their objective, and based on that. So this you have seen that the cesium zirconia, and if you have silicon carbide, and you can see that very smooth heating, and there is no plasma formation. Next slide, please. Again, the susceptor assisted microwave heating of zirconia. This is the part, and this is zirconia is another interesting material. I want to pause here. I want to explain what is zirconia. Zirconia itself is a susceptor, but it's a dangerous susceptor. Why? Because at room temperature, zirconia does not heat. It is like a father and son. Initially, son or kid is very, very young. Kid cannot walk. Father will teach the kid to walk. Father will be walking first, kid will be following. Kid will grow, and beyond a time, kid will run. Father cannot even run and follow. Who is the kid? Kid is zirconia, and father is silicon carbide. Okay, so silicon carbide is a global susceptor. So zirconia is like a high temperature susceptor. Beyond the time, you can see that, as I see at this point, the zirconia is line zirconia. It's like slow, it is slowly heating. But beyond the temperature, beyond this point, this 600 degree, you can see silicon susceptor is heating rate is cannot get heated more than 800 or 900, but zirconia can get peacefully 1200, 1300 degrees centigrade. It's a beautiful result. And this kind of combination, if you have a susceptor like zirconia, silicon carbide, that's an awesome susceptor assembly, and that can give dramatic heating pattern. So another is susceptor assisted microwave heating of Si3N4 pellet, the silicon carbide. These are all kind of similar stories. Next slide, please. Okay, next is there are some quick slides. So I'll just show you the different applications, including of aluminum SiC powder, and we can see using these are the contrasting situations where microwave heating is giving much higher heating rate compared to conventional identical situation. And you can see how microwave is heated faster, even conventional microwave for different kind of material. And yeah, so please go to the next slide. Yeah, it is a very interesting slide. I wanted to show here this. If you do for conventional, you have to go for 18 hours, but microwave can go for 7 hours. So, so you can get conventional sinter at 1600 degrees centigrade for 4 hours, and microwave you can get for 2 hours. So this kind of savings of time, and we can get uniform product quality that I'm going to address. I'm not going to discuss much on the experimental part. There are many things we have to. So our job was to highlight different papers and to see the enhancement and have a cute summary on the microwave assisted transport enhancement of the energy and of the microwave heating rate energy savings. So next slide, please. Yes, the microwave sintering of ferrites. You can see that the highlight processing time for microwave sintering is 3.5 hours, and conventional is almost like 3 times. You can see that. So these are the kind of, so these are even the product quality you can see is dramatic improvement. Processing time here 24 hours, and it's 25 minutes. You can see that how much dramatic enhancement. Next slide, please. So applications were actually studied for nickel, copper, zinc, ferrite, multi-layer chip inductors. Next slide, please. Barium titanate is all you have done the calculations here, the energy savings. Next slide, please. Microwave sintering of nickel electrode, barium titanate, multi-layer capacitors. You can see the quality of capacitor is pretty good with using the microwave compared to the conventional. And microwave is giving 1.5 to 2 hours compared to the conventional, which does not give a good quality. It takes 15 hours processing time. Next slide, please. Multi-layer capacitors, again, the same enhancement. I don't want to get into details. Next slide, please. Yes, the lead zirconia titanate, piezoactive films. Next slide, please. Or solid oxide fuel cells, a big challenge, SOFC. And there also you have seen dramatic enhancement. You need to have soaking period, that means heating period. You need to have only 30 minutes preheating period for microwave, but conventional you had 5 hours, and you can see dramatic change in the heating stuff. Next slide, please. Again, the anode supports solid oxide fuel cell SOFC. You have seen different kind of energy enhancement. Next slide, please. Quality enhancement by microwave sintering is another aspect. That is the way we can, in fact, conventional sintering and microwave sintering with the susceptor, we can have quality enhancement and also processing time enhancement, processing rate enhancement. So porcelain board is one of the examples. Next slide, please. Microwave processing of ores. So basically the gold business, you can always talk about the gold is a very good business, and removal of carbon is one of the big challenges. It can happen at high temperature, and carbon also is susceptor. So more carbon is good because it will absorb microwave, and high temperature carbon removal is also pretty good. And microwave found to be promising for the gold processing from the ore. Next slide, please. Yes, gold recovery. You can see my paper to have more such pictures, more understanding. Next slide, please. Yes, microwave processing of ore. There are many interesting characters. Next slide, please. Microwave assisted reduction of iron ore. This is another area we can look into, and all the heating applications for the processing quality, for the product quality and the heating rate enhancement. Next slide, please. Microwave assisted preparation of glass. This is another interesting area where microwave is found to be promising for the processing rate with susceptor, silicon carbide susceptor. Next slide, please. Semiconductors, another area. Next slide, please. Yes, intermetallic compounds.
Dr. Basak, 2 minutes.
Yes, that's what I'm going very fast. Yeah, it will be done in 2 minutes. Next slide, please. Yes, so Ni nickel chromium foams. These are the processing time. You can see that microwave 1 step and 3 step. Next slide, please. Yes, this is a setup we have done in our laboratory. So people challenge me, you cannot put metal in microwave oven. I said, yes, you can put metal in microwave oven. I did one of the PhD students' work. And how did I put? We have put silicon carbide, surrounded the metal, and metal could melt. You can see that, all molten metal. And there are 3 metals, tin, lead, and aluminum. These have been melted, and we have melted in the conventional burner and microwave, and we found dramatic enhancement, and we can see the process works. Yes, we can put the metal. That's the answer. Metal can be put bang on with the susceptor, done. Next slide, please. Okay, so SiC micro treater platform, these are the another applications. Next slide, please. This is taken from my paper, which has been top 1% paper in Elsevier for this energy. And you can see this is the energy savings. Because of that, people are using our design, using all the stuff from this paper. We can see 2016 paper. We can how the energy savings are, the processing times for conventional and microwave. Next slide, please. We also do the modeling, mathematical modeling in our group. These are the areas we have worked on. And we have also, people ask me, what's the mathematical perspective of susceptor? We have done mathematical analysis part. Next slide, please. And we have used the materials like beef and bread. Beef is having high dielectric loss and bread is a low dielectric loss. And we have found interesting mathematical result. I have not used any software. I have used only Photon 77 programming to get the results. So I am very much against using software, because software, we get good results, colorful results, but sometimes the mathematical viability is a big question. Next slide, please. These are all results based on our theoretical work with the susceptor application. Next slide, another 2 more slides. Yes, these are the archives. My PhD student worked on the metal melting, and we have also worked on the lot of review articles on my work, based on my work, and there one is published in the ICHE journal. Food Research International, food processing applications, energy, and critical reviews in solid state material science. So if you have any questions, doubts, you can actually look into these 4 papers, which will give enormous insights. Next slide, please. So this is the ICHE journal cover page. Just now I showed this was designed by us in 2012 article, and this is the cover page article. Next slide, please. And this is the energy paper, what I was talking today. This has become top 1% paper in engineering. And microwave food processing review article, what we have worked on food science, it has become top 1% in agricultural science, with just crossed 1,000 citations. And thanks very much for your kind attention for this presentation. Questions?
Yep. Questions?
Very good question. Different dielectric properties will be there if it is powder form or the rod form. We are doing we do experiments. In fact, there are network analyzers which will measure constant dielectric loss. So we prepare your material, put in network analyzer, it will give the dielectric loss, and you have to know what is the objective. So it depends, and also our market quality is very bad. There is no reproducibility. The company will go that, so we'll give you a good one. A lot of impurities will be there. So you have to have the benchmarking, a lot of experiment redone, and you have to get the result. What is one? Beta form. I don't know much of the characterization because I'm a heat transfer mechanical engineering kind of background. So I do only of the heating part like engineers. So we don't know much of the property characterization. But wastewater, I am telling you that is a hot area. When you have hospital waste, that does not absorb microwave. So what I suggest, I'll give you an idea. If you are talking about hospital waste, like the COVID time, a lot of hospital waste, you put silicon carbide powder, put in the microwave oven, dramatic, done. But if you don't put silicon carbide powder, it won't be heated. It will be just microwave waste. Yeah. So that's my work was basically, my focus was that I will use those materials which won't absorb microwave, but how to make it enhanced heating. That was the objective. Yep. Yeah. Yeah.
Okay.
A student question is first. I think, yeah, of course, because generally they don't. Please, student side here. Any questions? No. Okay. Then.
Okay. So it's good to see that you have tested some metals also in the microwave.
That is my PhD student's work. Yeah.
Tried any alloys for that matter, and did you observe?
No. Alloys, I don't know, but it should work because it is if you put a susceptor, anything you put inside, which can be heated up. But metal is dangerous. In fact, this project was rejected by CSIR, DST, and all the funding agency. They said not doable. I took the challenge. I said, okay, with my institute funding, I will do that project. They said your paper will be rejected. So it was rejected in all funding agency. And I can tell you that my all works are done with zero funding from DST. All done the funding with IIT Madras. I have not received any funding. Yeah, thank you.
Thank you, sir. Thank you for a wonderful talk. And now we would like to felicitate sir. So I would like to request Professor Krishna and Anthony, sir, please to come. I'm sorry.
I'll take a second. Good evening.
Yeah, good afternoon, everyone. We'll move on to the next speaker for this session. So the next speaker is Dr. S.K. Shukla, who is currently working as an associate professor in the Bhaskaracharya College of Applied Sciences, which is under the University of Delhi. He has earned his MSc and PhD degrees from DDE Gorakhpur, and he has published more than 96 papers in different journals, and also contributed to many journals. And in fact, he has also edited a book called as Advanced Carbon Materials and Technology for the publishers. He has got several awards, and he's also a reviewer of several journals. And some of his awards include the Materials Letters Award of 2012, International Association of Advanced Material Scientists Award of 2011. He has also got the bronze medal in 2011 from the Indian Association of Solid State and Allied Chemists. And he has also got this Dr. Lakshmi Awards in 2022. So he has several awards to his credit. And with this few words, I would like to request Dr. S.K. Shukla to deliver his presentation. Thank you, sir.
Thank you. Thank you, Chairman, for introduction and organizer for giving me opportunity to share some of the research work with you peoples. We already know that first polymers are synthesized in 1907 in the form of bakelite, and later on established as a feasible to synthesize a polymer in laboratory in 1920. And within 20 years, it got a huge market, and currently most of the materials are replaced by the polymers, whether it is the metals, whether it is non-metals, whether ceramic, each and every kinds of materials are currently is going to be replaced by the polymers. So this is the versatility of the polymers. So basic advantageous feature of polymers are low cost, processability, durability, and reusability. Apart from their positive features, they have some limitations, which are electrical conductivity. They are normally electrically insulating in nature in early phases. They have consumed their functional group, so they are chemically non-reactive. They don't have interactivity and functionality. These are the limitations which avoid the use of polymers in the active chemical applications. So in order to improve these problems, people try to functionalize the polymers. Functionalization means we add some reactivity by putting some compounds, and these are the basic features, basic methods by which we can make a polymer functional, and which is the grafting, doping, dimensional alignment, composite, and blending. The composite part has been already touched by the earlier speakers, Dr. Ajay Misra. So the addition of chemical functionality explore the polymers in application in different form, including the sensors. And these are some area where we use the functional polymers, including the sensor applications. When you try to use the polymers in the sensor application, sensor is an analytical device which is used for quantitative and qualitative presence of a chemicals as well as physical parameters. So the basic feature what we required in a polymer to make the sensor, they should have adsorption capacity, they should response, selective catalysis, interactivity, and chemical reactivity. Let me skip. So if you have to categorize the sensors, there are electrochemical sensor, optical sensor, mechanical sensor, thermal sensor, and gravimetric sensors. We have used our first chemically functionalized polymers in the sensing of the humidity. Although humidity monitoring is a very old practice to predict the rain, but in current scenario, the presence of humidity is very important in many different applications. One of the application has already mentioned by the previous speakers about the communication. Similarly, the packaging, comforts, and different area where humidity sensing is playing a significant role. This is our laboratory design simple setup. It is a glass jar where we have put a U-shaped glass tube and coated with some polymers and non-polymeric material. We allow to pass here helium neon laser, and the loud output which is coming, we monitors by some simple power meter. And inside this chamber, we put the saturated salt solution. There are several salts, potassium nitrate to lithium chloride, which are having ability to generate humidity of a desired level on the basis of their relative vapor pressures. So when a particular humidity level is going to generate, what happens? It is going to adsorb on the surface. The optical output power is going to be changed. So we monitor the change in optical output power at the different humidity level to explore its application in humidity sensing. So this is a simple result which we have published in 2004 by this instrument. So you can see as humidity level is going to increase, output power is going to increase. So this result can serve as a calibration curve to monitor the humidity level of a unknown place or a unknown chamber. Second setup, that is optical part. Second setup, which is very feasible to anywhere, we have put the electrochemical humidity sensing. We make a small glass slide, very poised, and it connected by the simple multimeter. And again, maintain the different humidity level and measure the resistance. So as the humidity level is going to increase, the water molecule is going to adsorb on the surface, and after adsorption, it generates hydronium ion and hydroxide ion, which allow the lowering in the resistivity of a material, and that change in resistance we can use for the monitoring of the humidity level. Here you can see as the humidity level is going to increase, the resistance is going to be increased. So again, we can measure by the optical method, and similarly we can measure by the electrochemical method the humidity present in a room or in a chamber. These are some more results which tells about the different humidity sensing ability of a different materials available in a place. Another important application of humidity sensing, we already know that when we exhale or inhale the air, if you are inhaling the air, it has a particular humidity level. But when we are exhaling, what happens? The humidity level is going to be saturate. So what we did, we have taken a commercial mask and put it the small film and connected by our multimeters. So when we exhale or inhale, allow to inhale and exhale. So that because of change in the humidity level, the resistivity is going to be periodically changed. So this change in periodicity of the resistivity because of change in the breathing pattern, we can monitor the breathing rate of a person where is a breathing in a right direction or it is having some problems. Another important work of the humidity, all of you observe, if you are having some problems, our breath is having some types of smell or some type of the air which is not good for our health. You can feel that our breathing has some smell. You can many people observe it. And one of them is the ammonia. If our kidney is not proper functioning, what happens? Our protein metabolism is not going to properly take place. So at that time, the ammonia level is going to be increased. So if we are able to monitor the ammonia level in our breathe out gases, we are in a position to pre-screen our kidney conditions. So here what we did, we allow to breathe a person and check the ammonia level in the exhale breath. So if it is going to increase beyond the level, that we can conclude that this person might be at the juncture of some problem which can be related to this protein metabolism or like some kidney problems. So this is the simple setup and this is our results about the ammonia sensing. We have used the polyvinyl chloride, polyaniline and clay composite by functionalizing by in situ polymerization of aniline in the solution of PBA by adding the clay as a filler. This slide is explaining that how humidity sensing is going to proceed. So first layer is going to have a simple covalent and second level is ionic and that is responsible for changing our resistivity or any other parameter we can also monitor. Many parameters can measure. We have measured the resistivity. You can measure capacitance. People are measuring the current. So different parameters can be measured by just adsorption. This is another sensing setup. My work focuses on sensing applications by putting some functionality in a polymer, and polymers are chemically inert and which is not having interactivity. So we have taken the polypyrrole and added the zinc oxide. So what happens? If you have put it here, you have taken the small glass rod and put here the coated particle and attach the two rods. We know we have used a lot of ammonia, urea in the soils as a fertilizer. But question comes, how long this fertilizer can be retained by the soil? This is a question. Because some soil is having long-term retaining capacity, some is having short-term because presence of the water. So in that case, you can take a small soil. This we have already done. All the apparatus are hardly 200 to 2,000 to 5,000 cost. You can prepare anywhere. Very simple setups. So you take the soil samples and put some moist water. So what happens? With the time, urea is going to convert into the hydrolyze and generate the ammonia. So when ammonia come into the contact, it is containing zinc. Zinc is having, you can see it is having the electron pair accepting capacity, which can cause Lewis acid. and ammonia is Lewis base. So electron pair is going to be transferred from ammonia to zinc. And because of this transfer, the composite is showing its change in the resistivity. So if you monitor the change, you are in a position to monitor the retaining volatile ammonia present into the soil, as well as to soil ammonia urea retaining capacity of the soil. This is the basic mechanism, and this is the effect of putting the zinc. And you can see if you are treating polypyrrole, it is not having very efficient, but putting the zinc oxide, it has its high sensitive applications. This is another kind of piezoelectric material people are using. If you put the some composite, but lesser work we have not done here. If press it, it generates some electricity, and that can be also used by the different kinds of sensor application. Another application which we have explored for the sensing applications, I have developed that adsorption and selective catalysis. As a student, all of you know, if you have to test the glucose in the lab, if you put the copper, it oxidizes glucose into gluconic acid. But question, if you put the glucose as such, you cannot make a layer, you cannot monitor long-term stability. So what we did, we have put the copper sulfate, make the composite of copper and polyaniline, and again coat it on the U-shaped glass rod and allow to come into the contact of the glucose. So glucose is going to be oxidized in the presence of copper and form the gluconic acid. And because of the gluconic acid and hydrogen peroxide, if you put some redox dyes, it's orthodienecidine, what happens? It is going to oxidize, it generates the bright pink color. You have to just measure the color intensity by using the same apparatus, which I've already discussed first slides. We are in a position to monitor the presence of quantitative presence of glucose in a natural or synthetic sample. When you talk about natural samples, you can take our blood serum, we can take our body fluid, any part, and when you synthetic fluid, we know that currently we are having a lot of processed juices. People are adding some non-edible sweeteners, which is not good for health. So you can discriminate whether it contains glucose or something which is not good for our health. So adulteration, we can check it here. So this is simple setup which we have designed in our laboratory, and we have also used for presence of the glucose, grape, mango, pineapple, and orange juices. I am skipping. This is for urea sensing. I will take this hardly 5 minutes. Last, people have talked about the presence of metals and many types of contamination. And we know how we can measure the presence of a metal. We need a very high cost apparatus, which is the atomic absorption spectroscopy, atomic coupled plasma spectroscopy, which are very costly. And same thing, you cannot have a portability up there. So what we designed, we have taken a simple glass chamber and connected with some polyelectrolyte membrane. So we attach with some potentiostat. And if we make a electrode of the polymer functionalized composite, the metal is going to attract, going to adsorb on the surface and have some reduction or some electrolytic interaction. Because of that, potential is going to be induced. And this potential, if you monitor different concentration, we have a calibration curve, and that can be used for the presence of a particular metal in a natural or water samples. This is the result which we have used for the presence of the copper after using the polyaniline and chitin, grafted chitin as a polymer composites. This is the method how we have prepared this composite. I have already talked about the selective catalysis. The metals work as a very good catalyst. So if we put some metals, and currently the huge access application of our pharmaceuticals or pesticides is a huge challenge because they are percolating directly our edible foods. So their monitoring is important. So what we have did, one of the pesticides is methyl parathion, which is used by different industries. So what we did, if we allow to come into the contact of copper, it oxidizes and generate the potential. And this potential can be used for the presence of a methyl parathion in a edible or natural or synthetic samples. We have also used for the presence of paracetamol in the water samples, and which we have taken from the hospital wastewater as well as urine samples of a person who has taken the paracetamols. This is another important, this is my last part. Everybody talk about the sensing of a metals. But what happens after the sensing? What is next? It is not the thing. So what we have done, we have taken the 3-chamber setup. So 2 chambers is 3rd chamber. So we put the electrode where the metal is going to be attract here, adsorb here. After sensing, we put it to the 2nd chamber and applied the external potential. So after a certain potential, this metal is going to be reduced. And after reduction, we can recollect, or it's the many small types of it. We call it extractive potentiometric sensing setup. We have used for lead and the chromium, 3-4 metals we have used it. Mercury, we have same setup, we have for sense it, and again we are going to recollect it. This is the mechanism, how we can do it, how this sensing process is going to be. Last, we have used the same chambers. People start talking about the presence of the wastewater treatment, because water is a very important ingredients. So what we have taken, this is our college sewage water. We have put it here and taken the chitosan and polyaniline grafted polymer composites. So polyaniline is a conducting polymers and chitosan is a biopolymer. When we have biopolymer, it allows the growth of microbes. So in this condition, we put our sewage water of our college and put some E. coli. Because of the biopolymer, the colony of E. coli is going to grow very faster. And that's why this organic water, organic content here oxidizes and going to be produce the current and voltage in the form of different pH. So we can use this setup for generation of current.
Can you please conclude your talk?
This is the last slide. I have already taken, I'm making only slide which is possible in 30 minutes.
Sure. Thank you.
So this we can use for microbial fuel cell to treat the water to generate the current and same time to purify the water in order to use in a normal application, not a drinking applications. So last, we have made the functional polymers and for different application which I've listed here. Last, I like to acknowledge my colleagues and some funding and my collaborators. These are my some more publications in this area. If you are interested, you can go through it. And I like to thank you for presence here.
Thank you very much, Dr. Shukla. It was a very interesting talk, and this gave a view that with minimal experimental facilities and with the minimal funding, we can do a lot. And it's really, really impressive, your presentation. Now the presentation is open for discussion. Questions from the audience, please. You may just put up your hand. Yeah.
Sure.
Sir, in jar system, you mentioned a U-tube which is connected to a jar to sense the humidity. So I want to ask that which material is used for to make that U-tube?
It's a glass. It's a glass. You take a, perhaps you go into your labs. I'm telling you, I'm a college teacher. And we don't have such facilities as IITs and other people's have. So that is why I planned all the setups we made in my labs. And none of the setup is more than 2,000 to 5,000. More than 2,000 to 5,000. Anybody can do it. Anybody. I open for demonstration. I have already demonstrated many places. Many places I demonstrated these apparatus. So you go into you take a glass rod you normally have in the lab and don't do anything. Burner, put the burner and heat it and just mold it. You use it. And same thing, you connect problems where comes. When you put into some glass chamber, you have to make a drill. And then you connect by the receivers of the power meter. So there is some connectivity. So that's a glass tubes, simple glass tubes.
Okay,
I
sir,
think
thank
I
you.
have cleared.
Anyone quick question? Anyone else? Not, let's thank Professor Shukla again for a very interesting and a very nice work. Thank you very much, sir.
Thank you, sir. Thank you.
Thank you, sir. Now we would like to felicitate Professor Shukla. So for that, I would like to invite Professor Krishnan and sir, please, Basil, sir, please. So for this, the session is over and we are really thankful for all the speakers and the chairperson. One of the chairperson was, getting delayed, so he had to leave in the between. But I thank you, Professor Krishnan, also for taking up the charge. And I request everybody to take a picture, please. We would like to take one group photograph, sir. So I hope you don't mind. Please, everybody come for a group photograph. Thank you.